Hey everyone. The topic that we're covering today is called equivalent systems. So we're going to start looking at equivalent systems by looking at a beam. And this beam is a horizontal member that is 8 feet long. Point A is on the left end. This point C is at the other end, the right end. And then point B is in the middle. And this beam is being subjected with 3 different forces. A 10-pound force up at A, a 15-pound force going down at B, and a 25-pound force going up at point C. And here is my XY axis to show the orientation. So if we were curious about what's going on at A, and we wanted to find the resultant at A. The word resultant to us before you entered statics and up till now has always meant the resultant force. But now the term resultant actually means the resultant force and moment on a system. So if a problem asks for what is the resultant of this problem, you would be finding out what the resultant force and the resultant moment is on the system. So previously, we were only looking at the word resultant meaning force, but no longer. From now on, whenever we use the word resultant, we mean the resultant force and the moment on the system, which when you have a resultant force causes translational motion, which we have also referred to as linear motion. And the moment causes rotational motion. So we're looking at the resultant, we're trying to find out, well, is it being pushed or pulled? Is there some kind of linear motion? And also, is there a rotational motion? Well, of course, in statics, our resultant is always 0, right? Our resultant is 0. There's no translational motion and there's no rotational motion. But in still dealing with equilibrium systems, equivalent systems, we're still dealing with the whole idea of moments. So looking at this problem, in terms of point A, I want to know what is the net effect on point A of the forces that are shown. So again, we have 10 pounds up, 25 pounds up, 15 pounds down in different locations. And I want to know what is the net impact of these loads on point A. So on point A, you may have said, oh, well, what's the resultant force? Right? Let's do it this way. Let's say the sum of the forces, and in this case, the sum of the forces happen to be in the Y. So we have 10 up plus 25 up minus 15. And so the resultant force in the Y is 20 pounds going up, right? Or we could say 20 pounds positive in the J, and the units are pounds. So this is our resultant force. So my resultant force was, I added the 10 and the 25 going up, subtracted the 15, and in the end, I have my resultant force of being 20 pounds going up. How about the resultant moment, right? So I'll write resultant force is this. And now the resultant moment. So we did the resultant force, and now we're doing the resultant moment. I'm going to change so we could see everything. And let's focus. because we're not going to see everything on one page. Let me slide this down. So if I wanted to calculate the moment, what axis is the moment about? All the forces and the distances are in the XY plane, so the moment's going to be about Z. So when I find the sum of my moments, it's going to be about the Z axis. And now let's figure it out. Let's use the right-hand rule. The 10-pound force is not going to create any moment about A because it's going through A. But the 15-pound force is going to create a moment of 15 times 3, because 3 is the perpendicular distance to A. My fingers go down in the direction of the force, palm goes towards A, and it's negative. So it's negative 15 times 3. And then what about the 25-pound force? Well, 25, the perpendicular distance is 8. So around point A, it's going to be 25 times 8. Put my fingers in the direction of force, palm towards the point I'm finding the moment about, and I get a positive. So we have a negative plus a positive. And what does this turn out to be? This turns out to be 155 K. And what's the units? The units are foot-pound. Foot-pound. And it's a positive, and it's in the K. So I'm going to write this down right now. Sum of the moments about Z. So the net effect of these three forces on this beam, or rather on the beam at point A, is a sum of the forces of 20 pounds going up and 150 foot-pounds in the K, in the positive K. So now let's take a look at equivalent systems. Here's my first system. 8-foot beam, 10 up, 25 up, 15 down. And we learned that the resultant was a sum of the forces in the Y, which turned out to be 20 K pounds. And the resultant moment about the Z was 150. In fact, you know, the fact that I'm writing some of the forces in the Y, I'm just going to keep the J out. £20. And some of the forces in the Z was 155 foot-pound. This was the resultant. Well, let's take a look at this. Let's look at system 2. System 2, instead of putting all three forces on, I just put the resultant force of 20 pounds, and I put a concentrated moment. I'm calling it concentrated. You remember that adjective concentrated. All these forces are concentrated, right? Because they're acting at a certain point. This is a concentrated moment. It's acting at that certain point. What it is, it's like as if I'm putting a screwdriver in here, and I'm turning the screw, and it's spinning right at that point, and I'm putting a concentrated moment there. Does system 1 equal to system 2? At point A is experiencing the 20 pounds just as it is in first system. It's also experiencing a positive moment of 155. It's the same. These are equivalent systems. Because point A, in this case, we're trying to find equivalent systems at point A. Point A is experiencing the same translational motion and the same rotational motion, right? Because the sum of the forces in the Y leads to linear motion, and the sum of the moments in the Z is rotational motion. And that's the same thing that I'm experiencing in system 2. It's the same beam, 8 foot wide, but now I'm putting the concentrated force, I'm putting the resultant force at the point, and I'm also putting the concentrated moment there. Those are two equal systems. Let's take a look at the third system now. Again, I'm trying to figure out, is this an equivalent system to these other two? Well, the resultant force of 20 pounds is still up, and it's placed at a certain location. It's placed at 7.75 feet from point O. If this force is at a distance of O, can I calculate the moment about Z? it would be 20 times 7.75. Fingers go in the direction of the force, palm goes towards the point. I would get a positive moment. And again, it's foot-pound. So the sum of the moments here, 20 times 7.5 comes out to 155 foot-pounds. So is system 3 an equivalent system? Yes. Why is this important? System 1 may not be that much of a complicated problem for you. It's only a beam that's horizontal, and there's only 3 forces on it. No big deal. But in statics, we could get very complicated. But what I did is I took this and I simplified it to an equivalent system, simplified it to equivalent system where I only have one force in one moment causing the same exact condition to point A. And this is the same thing. This is also simplified. Instead of having these 3 forces on this body, I just put one force on it, which is the resultant force, and I put it over at a distance from A to create the same moment. Okay. So again, in statics, we have complicated problems and we could simplify those problems. Okay. This one in green. This one in green is called a force moment problem. And the reason that it's called a force moment problem is because they are taking a complicated system and reducing it to a force and a moment at a point. It's called a force moment problem. This one, as you probably could expect, is not called a force moment problem, but it's called a force location problem. Because it's showing a force at a certain location that is equivalent to the complex system. So I'll draw down from this red one. This is a complex system. But these are all equal. These are all equivalent systems at point A. Okay. And I have to say at point A, because if I was looking at a different point, these would not be the equivalent. System 2 and 3 would not be equivalent to 1. It's only, these 3 are equivalent because we're looking for an equivalent system about a certain point, and in this case, it's point A. All right, so again, we're taking a complicated problem and reducing it, simplifying it to one of 2 different things. One is reducing it doing a force moment problem. The second one is a force location problem. So let's go on now to the problems that we have in class. Okay. Let me put it in focus. So the first, is this a 2D problem or 3D? 2D. The next problem, 2D or 3D? 3D. And the last problem here, 2D or 3D? 3D. So we're going to be working on 3 different problems, 1 2-dimensional problem and 2 3-dimensional problems. But we first need to know, we know that we're working on equivalent systems. Oops, equivalent systems. But we need to know which kind of problem it is. So let's read it. It says, replace the 3 forces shown by an equivalent force couple system at point B. Now, many statics textbooks, once they teach you couples, which you just learned about, and we know couples are 2 forces going in opposite directions, but they create a moment. Sometimes they wind up using the word moment, couple synonymous with moment. But the question says, replace the 3 forces shown by an equivalent force moment system. So what kind of problem is this? Is this a force moment problem or a force location problem? It's a force moment problem. because they're not asking you for the location of the force. So it's a force moment problem. And just as we did with this complicated problem that was given initially, we found the resultant force and the resultant moment, and we're going to do that here too. So the first step is to find the resultant force. And in this case, our resultant force looks like it has an x and a y value. So my resultant force in the x, it's negative 100 I, and then it's minus 100 j. And the units are in pounds. And that we just expressed it in vector form, but we know also there are times that we want to express it in maybe in magnitude and direction. So force is equal to 100 squared plus 100 squared under the radical. Does it come out to be 141.4 pounds? And then when I solve for theta x, which you know how to do already, so I'm not going to show the steps, it comes out to be 135 degrees, and theta y turns out to be 135 degrees. So now let's do some checks. Looking back at the picture, yeah, the force in the x is negative. And yes, looking at these two forces in the y, the resultant is negative. And it does make sense that these are both obtuse angles because they're negative values. And let's see, if I were to draw this force, it's going in, let's just put x and y here. We know it's going in the negative x and the negative y, right? So it's going down like this. Our force is going down in this direction. Okay, and then the next step is to find the resultant moment, and we know because all these forces are in the x and y plane, we know the moment is going to be about z, and they want to know the moment about point B. Okay, so here's B. So the 100, it's 100 times 10, perpendicular distance, I'm getting a positive. It's 300 times perpendicular distance is 14. Put my fingers in the direction of force, palm towards B, it's a negative. And then 200 times 8 plus 12, so that's 20. Fingers go in the direction of force, palm goes towards the point B, it's a positive. And in the end, this comes out to be the sum of the moments about point B is equal to 800 inch-pound, and it's positive. And we know it's in the z direction. So now, first step, we found the resultant force. The second step, we found the resultant moment. Okay, and now I'm going to erase this over here. Now, the third step is to draw it. So we have a bracket, and I'm going to draw this in pencil, actually. Well, I'll just go up here. We have this bracket, and it's 8 inches here, 10 inches here. Here's A, here's E, here's B, and I'm going to zoom in. And what I learned is, because this is a force moment system problem, go back to our example, in a force moment problem, I am going to draw the force and the moment at the point that was in question. The point at question was B. So at point B, I'm going to draw the force, and we know it's going in the negative direction. It's going in the negative x and the negative y direction. And I could put my angle here if I want. I could put, let's just put the angle. Here's my resultant force. It's 141.4 pounds. And let's just draw the angles. The angle right here I guess I should probably draw it off the beam instead. Probably would look clearer. This is 45 degrees. So I know this force is going down negative x and negative y. The magnitude is 141.4 pounds. And the angle of it here is 45 degrees. But also at point B, I have a moment, and the moment is positive. So I'm going to draw my moment, and the moment about B, Z, is equal to 800 inch-pound. So in addition to drawing the resultant force, I'm just drawing the resultant moment. So we took a problem, a 2D problem that was a little more complex, and we wanted to reduce it to a force moment system. The first step was to find the resultant force. The next step, second step, was to find the resultant moment. And the third step is to draw it. Draw the force, the resultant force, and the resultant moment at the point in question. So in the end, this system here is equal to this system right here, where I have a force and a moment at the point. It's equal to this, and it's simplified because now I only have a force and a moment. Okay, let's jump down next to the bottom 3D problem. So let's see what's going on here. So it says, forces are applied at point A, point B, and point C of the bar shown in the figure. Replace this system of forces with a force R, a resultant, through point O and a couple. Again, what did I say earlier? Some statics textbooks start to use the word couple when they read moment, when they mean moment, because a couple creates a moment. I think it's ridiculous, but it's done. So what type of problem is this? Again, what kind of problem? It's a force moment problem. Actually, you know what? Before we go on to this 3D one, I think I want to go back to the 2D problem and figure out what we would do if it was a force distance problem. Okay? So I'm going to pull out some engineering paper. And we're going to do this as if, so this problem is not out of your textbook. So we're looking at the same problem, right? But instead of solving it for a force moment problem, we're going to do a force distance problem. Force location problem, rather. In force location problems, the steps are the same. First, find the resultant force. And we did already. We found that the force is equal to negative 100 I minus 100 J pounds. And also the magnitude is equal to 141.4 pounds. And theta X and theta Y were both 135 degrees. Okay. The second step is to find the resultant moment, which we did also. We found that the sum of the moments about point B through Z was 800 inch-pound. So in a force location problem, let's look back at the ones we originally showed, or I showed. Here's the system initially given. Here's a force moment problem, and here's a force at a certain distance that creates a moment. Okay. So here, I have the resultant force and I have the resultant moment, and we've done this before. How do we find the perpendicular distance? So the third thing is third step is find the perpendicular distance. And how do we do that? We know that, right? Because we know that the moment is equal to the absolute value of the force times the absolute value of the perpendicular distance. So therefore, the perpendicular distance is the absolute value of the moment divided by the force. Okay? And in this case, the moment was 800 and the force was 141.4. And this value comes out to be 5.66 inches. The fourth step is you have to draw it. You have to draw the one force at the distance. So going back here, we have a force that's going in the y, and the perpendicular distance to point A was in the x, and the moment was about z. Here, our force is not in the x and y, it's in a combination of both. And we already said that the force goes down at a 45-degree angle. And the force is 141.4 pounds. So I'm going to draw my bracket. "10 inches. And this is 8 inches. And this is 12 inches. And this is point B. Remember, B is the one that's important for us. This is point A. And this is point E. And we're drawing my X and Y axis. So this force we know goes down to the left. It has a negative X value and it has a negative Y value. And the distance has to be away from point B. And we learned that the distance is 5.66. So where can this force go? Remember, it creates a positive moment about B. So in order to create a positive moment, a moment going in the positive direction, where should this force be? Should it be on the left of the bracket? Does that create a positive moment about B? Or should it be here that it creates a positive moment about B? Which location? This location to the left or to the right creates a positive moment about B? It's to the left. So that means that this force has to be drawn somewhere here, and it's 141.4 pounds. And I'm going to just erase this now. And I know that the perpendicular distance I counted is 5.66. So I have to draw a line perpendicular from point B to the force, and this distance right here is 5.66 inches. That's the perpendicular distance. Okay, so here's the force, and it's at a distance of 5.66. Okay, so let's just go back to this first problem. In this first problem, they asked you to find an equivalent system that was a force moment system. So the first step, number one, was to find the resultant force. Second step was to find the resultant moment. And the third step is to draw both the force and the moment at point B. Now I said, okay, well, what if they had asked you for a force location problem? Well, you have to do the same steps. You find the resultant force, the resultant moment, but now we have an additional step. They want to know the location of where that force is. So we solve for the perpendicular distance, which came out to be 5.66. And then the fourth step is draw. So for both of them, for both of these equivalent system problems, you first have to find the resultant force, then you find the resultant moment, and then you have to do a drawing. But for the location problem, you have an intermediate step of having to find the perpendicular distance. Okay, absolute value of the moment over the absolute value of the force, 5.66. And then you have to figure out in the drawing where the force is. You put it in the direction it's going. It's in the negative x and negative y. You put it in the direction it's going, and you have to find which side of the point it's on to create that positive moment. I'm going to erase this moment. Because in this kind of problem, a force location problem, I'm only drawing the force at that perpendicular distance from that point. Okay? So now let's go back to the third problem. Okay, so this one we saw was, so this problem, if you see, it's a 3D problem, and it's asking for replace the system of forces with a resultant force through point O with a moment. So this is a force moment problem in 3D. And now this problem, determine the resultant of the parallel force system, locate the intersection of the line of action, the resultant with the XY plane. So what kind of problem is this? This is a force location problem. So we're going to do one 3D problem, force moment problem, and one 3D problem, force location problem. And I'm going to do it on here because I'm going to need more space. So this is problem 4.147. Remember, it's not in the textbook. I want to give you extra examples. This is a problem, but this page is in your equivalent system module. So we have all these forces. So let's see. We have 225 force. We have a 125 force. We have a 175 force. We have a 150 force, and we have a 200-pound force. So what's the first step? First step is to find the resultant force. And what's the resultant force? Let's see. On a 3D problem, we always have to look at the axes. Here's x, here's y, and here's z. So let's see. Forces in the x. The only one in the x is this one. So it's 175I. In the y is this one and this one. So it's plus 350J. And then we have a 125 up and we have a 225 down. So that's a minus 1K, and the units are all in pounds. Right? And then if I want to find what the resultant force is, I would do, let me see, I'm pretty sure I did this math already. Maybe I didn't. Okay, so you'll have to check me. So 175 squared plus 350 squared plus 100 squared equals all into the radical. It comes out to be 403.9 pounds. And then let's find out the theta y, theta z, and theta x, y, and z, which we already know, right? It's the inverse cosine of the force, the x component over this. So let's just see, 175 divided by 403.9 equals inverse cosine 64.3 degrees. Next one's 350 divided by 403.9, inverse cosine 29.9 degrees, and 100 negative divided by 403.9 equals inverse cosine 104.3 degrees. So now let's do our check. 64.3 cosine squared plus cosine squared 29.9 plus cosine squared 104.3 equals 1. Let's check it out. And then the acute obtuse checks out because x and y are positive, so they're both acute. The z is negative, so it's obtuse. Okay. And now let's check out 64.3 cosine squared plus 29.9 cosine squared plus 104.3 cosine squared Yep, comes out to be 1. Great. So the first step is to find the resultant force. Next step is to find the resultant moment. Okay, ready. So looking at the picture, you want to do vectors or right-hand rule? Right-hand rule. So I'm going to make a table. Table, table, table. This is going to be all the forces. Here are the moment and x. Remember, we're trying to find, what are we trying to find? We're trying to find it about O. So here's our axes. Good, our axes is through O. Great, we don't have to redraw our axes. So we're finding the moment about O in the x-axis, moment about O in the y, moment about O in the z, and the units are going to be inch, pound, inch, pound, inch, pound. And now how many forces do we have? 1, 2, 3, 4, 5. And in addition, we want a total. So I'm making 3. This is my total. So let's do 225 pounds, and let's do forces all in pounds. 25, 125, 175, 150, and 200. Remember, where this is all absolute values, right? The 225 goes in the z. The 125 goes in the z. The 175 goes in the x. The 150 goes in the y. And the 200 goes in the y. So to start, if 225 goes in the z, it's going to create no moment about the z because it's parallel. This is in the z. This one's in the x. This one's in the y. This one's in the y. Great. Okay, are there any intersecting? Let's look at the 225. The 225 intersects the x-axis, so 0, no intersection there. No moment there. So let's just stick with 225. It doesn't create a moment about the z because it's parallel. It doesn't create a moment about the x because it intersects, but it does create a moment about the y. So we're trying to find the moment about the y, and the force is in the z, so the distance is going to be in the x. The distance is 20. So 225 times 20. And let's see, fingers go in the direction of force, palm goes towards y-axis, I got a positive. Okay, let's look at the 125. 3D spatial visualization. See how this bar comes out from the origin? This is horizontal. How do I know it's horizontal? The line 22 and this bar are parallel to the y-axis. It's horizontal, and then this is vertical. It's vertical, this. That means point C is coming out at us, okay? So it does not intersect the y, and it does not intersect the z. So it is going to create a moment about it doesn't intersect the x, I meant. So let's see. Moment about x. So I have the 125. The 125 is in the z. I'm trying to find the moment about the x. The distance is in the y. It's 22. Fingers go in the direction of the 125. Palm goes towards x. I got a positive. Okay, 125 about y. Remember, this whole bar is out from the y-axis. If the force is in the z, we're trying to find the moment in the y. The distance is in the x, and here it is, 20. So it's 125 times 20. Fingers go in the direction of the force. Palm goes towards y, and I get a negative. Okay, 175. 175 is parallel to x. It creates a moment about the y. How far up is it? Look at this. You got to look close. This bar is 22 inches up. Hang on a second. Let me just make sure I didn't make a mistake in the other one. No. Okay, this 175 is up from this bar. This bar is 22 inches up, and the distance to C is another 10, so it's 32. So it's 175 times 32, 175 times 32 about the y, fingers go in the direction of the force. And does that make sense? If the 175 is in the x, I'm trying to find the moment in the y, the distance is going to be in the z. 175, fingers go in the direction of force, palm goes towards y, I got a positive. Next, 175. I'm trying to now find the moment about the z of this 175. This point is right over the x-axis. If the force is in the x, I'm trying to find the moment in the z. The distance is in the y. It's 175 times 22. Fingers go in the direction of force. Palm goes towards z, negative. Okay, 150. 150 is in the y direction. I want to find the moment about the x. So it's 150 times, it's 22 up, 32. Again, the 150 is in the y. I'm trying to find the moment about the x. The perpendicular distance is the z. So it's 10 plus 22. Fingers go in the direction of the force. Palm goes down towards x, and I get a negative. And then I have the 150. Finding the moment about z, here's z. 150 is in the y. Z is in the z. And the distance has got to be in the x. How far is this out? It's out 20. So 150 times 20. Fingers go in the direction of 150. Palm goes towards z, and I get a positive z. Okay, we have the 200 left. So 200 is in the y. I want to find the moment about the x. So I have to use the z distance, 22. Fingers go in the direction of force. Palm goes towards x. It's a negative. 200. This may be overwhelming, but the math's a lot different, a lot easier than doing everything vectorially. In any event, this is what you're doing it by right-hand roll. You got to get better and better on this. Okay, 200 pounds is in the y. I'm trying to find the moment about the z. The distance is going to be in the x. It's 20. Fingers go in the direction of the force. Palm goes towards z, and it's positive. So let's do all the calculations now. 125 times 22 plus 2750. 225 times 20. 450. 25 times 20. Is that right? Let's just try it again. Times 20. 125 times 20. Yeah, got a 0, too many zeros. 175 times 32. 5600. 175 times 22 equals 3850. This is going to be 3,000. This is 4,000. 4,400. 150 times 32. 480. This is positive, negative, negative, positive, positive. Okay, this is a long problem. 2750 plus 4800 minus 4400 negative 6450. 4500 minus 2500 plus 5600. 7600. 3850 minus plus 7,000. 3150 plus. So that means that the moment is equal to negative 6450I plus 7600J plus 3150K. And it's all in inch pound. And let me just check to see if I do actually have this problem. Negative 640. Yeah, I did it already. Okay, all right, and now our moment, I'm going to get the magnitude, use the vector, now the magnitude, and I'm just going to write the numbers down. The magnitude comes out to be 10,454 inch-pound, and theta x comes out to be 128.1 degrees. Theta y turns out to be 43.4 degrees, and theta z turns out to be 72.5 degrees. And then I do my check. Cosine x squared plus cosine y squared plus cosine z squared. And it does come out to 1 because I've already checked it. And then I also want to do the acute obtuse. And does that make sense? I have a negative x, it's obtuse, and the other acute. Okay. Okay. What were the steps in a force moment problem? Remember, back to this problem. First step, find the resultant force. Second step, find the first resultant moment. And the third step is to draw it. So I found the resultant force already. I found the resultant moment already. And now I have to draw it. So again, practicing in 3D. Here's the y, here's the z, here's my x. So here's point O, and we're finding the moment about point O. And so we have our bracket. This bracket is in the XY plane, and it's going up 22 degrees, 22 inches, and it's coming out 20 inches. So let's just say here's my 20 inches. And it's going up 22 inches. I'm going to write NTS because I'm not drawing it to scale. And let's say right here. So this is 22 inches, and my bar comes up here. And then it stays horizontal. So horizontal, if it's horizontal, it's parallel to the y-axis. Here's the point. So it's going to stay right there. And how much is it coming out? It's coming out 22 inches too. And then it goes up 10 inches. And let's see, what other dimensions do I have to include? I got the 22, I got the 20, I got the 22, I got the 10, I got everything. Okay, so this beam, or not beam, it's a bracket or a bar. This bar is like this, it's like this, and like this. And it looks much different than what's drawn here. Why? Well, one, this is not quite an oblique, but it's not quite a isometric either. But mine is definitely oblique. But the important point right here is the point that we were trying to find the moment and the force about. So this is point O. So let's draw it. I have a force of 175 in the eye. So force X is equal to 175 pounds. I have a force Y, it's also positive. Force Y is equal to 350 pounds. And force in the Z is negative. It goes down 100 pounds. Then I have to draw the moment. Let's draw the moment in green, I guess. So my moment that's created because of this force is a negative 6450 around the x-axis, so it's negative. If I put my finger in the direction of x, and if the force was positive, it would be spinning that way, but the force is negative, so it's going around like this. And that moment around the x-axis is 6450 inch-pound. Okay. Okay. How about the y-axis? So the y value is 76. It's positive. So my finger, I'm putting my finger in the positive y direction, and it comes around this way. So here's the moment about the y, and it's equal to 7,600 inch-pound. And then in the z, it's 3150, and it's positive. Finger goes in the direction of the positive. It's coming around this way. And it's a moment about the z, and it equals 3150 inch-pound. So this is a very long problem. It started out as a problem where they were asking you to find an equivalent system through a force moment problem. You first found the resultant force. You next found the resultant moment. And then the third step is to draw it. Now, let's do the third problem. Okay, it says, determine the resultant of the parallel force system shown in the figure and locate the intersection, so we know it's a force location problem. So what's the first step? For 4-130, the first step is find the resultant force. What's the resultant force? The resultant force, oh, nope, look at that. I jumped ahead and put y. Take a look. Whenever it's a 3D problem, you have to look. This is the x. This is the y. And this is the z. So the resultant is in the z. Let's see, they're all going down. 5, so I'll just do it. 500 plus 400 plus 300 plus 200. And they're all in the negative z direction, and it's all newtons. So the resultant force is negative 9, 10, 11, 12, 13, 14. 1,400 newtons, and it's in the negative k. So first we find the resultant moment, force. Second, find the resultant moment. Well, let's think. I'm going to do a sketch. Here's my z-axis. Here's my y-axis. Here's my x-axis. And this plate is like this. It is, let's see, 500 millimeters here. Oops, I should have still not drawn to scale, but maybe I could draw it a little bit better. And this is 1,000 millimeters, right? So this distance right here is 1,500. And this is 1,000. So we just learned that the resultant force is going down. What moment? Oh, and it says they want to know the location, right? It's a location problem. They want to know what the location on the XY plane, so off the X and Y axis. So if these forces are all in the Z, does it create a moment in the Z? No. Do these forces create a moment about the X? Yeah. And do they create a positive or negative moment? Put your fingers in the direction of all the forces, palm towards X. They create a negative moment about X. What about Y? They create a negative moment. No, a positive moment about Y, because all the forces are trying to twist the X-axis this way. Okay? So in this case, we found the resultant force. Now we have to find, right, resultant force. Now we have to find the resultant moment. And the moment is in both directions. So let's do the sum of the moments about the x first. So I'm trying to find the moment about the x-axis to these forces. And maybe I should zoom in a little. You can see the picture better. Focus it. So the first force is 500, and the perpendicular distance is 500, and it creates a negative moment. The next one is 400, and the perpendicular distance is 1,000, and it creates a negative moment. The next one is 300, perpendicular distance is 1,000, negative, and then 200 times 1,500, and it's also negative. So the sum of the moments about the x turn out to be negative 1250 Newton millimeter. Let's do the sum of the moment in the y. And again, I can do this vectorially, but I want to do right-hand rule because I want to get more comfortable with it. So the moments about y, well, the 200 creates no moment because it intersects. So the 300 times 500, positive. 400 times 1,000, positive. And 500 times 1,000, and it's positive. And the sum of the moments about y come out to be 1050. Okay, so if I wanted to draw the picture, I'm going to zoom out now. This is a force location problem. First thing, find the resultant force. Next step, find the resultant moment. Third step is to find the perpendicular distance. Well, how are we going to do this? Because we have both an x and a y value. And in the past, these have been the hardest type problems for students. Okay, so let's think about this physically. This force here is negative 14 in the k. It's going down somewhere, right? If it's going down, and we also learned that the x moment is negative. So if it's negative, it's creating a negative 1250 Newton millimeter. And here in the y, it's creating a positive. Let's make this axis a little bit longer. It's creating a positive moment. The moment about the y is 1050 Newton millimeter, right? So did I draw that in the negative z? Wait, x. So we have a negative moment here. We have a positive moment here. Does this force in this position create this moment? Does a force going down on this plate create a positive moment about y? Yes, it spins it down. And does this force location create a positive? It creates a negative moment. So the force goes down. I have a negative x moment, a positive y moment. And how am I going to find the perpendicular distances? Well, aren't we looking for this distance here and this distance here to locate? Oh, I didn't draw that line parallel. I'm looking for these two perpendicular distances. And how we can't use the same variable, right? We know that the the perpendicular distance is equal to the absolute value of the moment over the absolute value of the force. Well, if I'm trying to find this perpendicular distance, that's in the y, isn't it? And this perpendicular distance is in the x. Do you agree? This is in the y and this is in the x. So let's find the perpendicular distance in the y first. Well, the perpendicular in the y is the one that this force, which is 1,400 newtons, is 1250. Actually, I'm going to write out the variable first. The moment about x and the force is in the z. Take a look at this. You know this already. If the perpendicular distance is in the y and the force is in the z, it creates a moment about the x. Okay? Because the only vector that's perpendicular to both y and z is x. So the perpendicular distance in the y is going to be moment about x, which is 1250, over the force, which is 1400. And the perpendicular distance in the y turns out to be 893 millimeters. So this right here is 893. And then the perpendicular distance in the x is going to be equal to the moment about the y over the force in the z. Again, we know the force is in the z. We know the force is in the z. We're trying to find this perpendicular distance in the x. Wouldn't you say that to find this moment, it would be 14 times this? So this turns out to be 1050 over 1400. And perpendicular x turns out to be 750 millimeters. And what's the fourth one? Draw it. And we did already. We have the force going down here of 1400. And then we're showing the perpendicular distance in the y here and the perpendicular distance in the x. And that's to create this positive moment about the y and the negative moment about the x. So what I have to draw is I have to draw, because it's a force location problem, I have to draw the force at a location. Okay, so let's just sum this all up. Starting from the beginning, in statics, many times complicated systems are given with a whole mess of forces, and we could simplify that type of problem into two different types of problems. We could take all these forces and reduce it, simplify it to a force moment problem, where I have a force and a concentrated moment at the point in question, or I locate a force at a certain distance. So these are two equivalent systems to this. This is a force moment, and this is a force location. And then we went to these three problems. In the first problem was a 2D. They asked us to find the equivalent force couple, which meant it was a force moment problem. Find the resultant force, find the resultant moment, and draw the force and the moment at the point. And that was exactly the same we did in this third problem. In this third problem, down here, the 3D problem, where we had a bar, and the first thing we did is we found the resultant force, we found the resultant moment, and then we drew the force and the moment at the point in question. Then we took this problem and we said, well, what if it was a force location problem? So what did we do? Again, first step, found the resultant force, found the resultant moment. But when it's a force location problem, you have to find the perpendicular distance, and you do it by moment divided by the force. And then the last thing is you draw the force at the distance. And that's the same thing that we did on this problem. It was a force location problem. First step, find the resultant force. Second step, find the resultant moment. Third step, find the perpendicular distance. And the fourth step, draw the force at the location. Okay, I'm going to stop now.